Right. Looks like we are ready to get started here. Hello again, and welcome to today's webinar, Constraint-Driven Design with OrCAD Capture. Again, my name is Michelle Spang, and I will be your moderator for today's webinar. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you are unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat, and we will do our best to resolve any issues. Everyone's line is currently muted and will remain so throughout the duration of the webinar. This will be an interactive webinar with poll questions throughout the presentation. Please take a moment when the poll questions are launched to provide some feedback to help us provide you with the most useful information. If you have any questions throughout the webinar, please type them into the questions panel as they come up. We will have EMA representatives available to answer your questions directly during the webinar. Assuming we have time at the end of the demonstration, we will field some of these questions in a formal Q&A. This webinar will be recorded and posted on EMA resource page. Once this is posted, we will send everyone who is registered for today's webinar an email with a link to the recording in the next couple of days. That being said, I want to thank you all for joining us for today's webinar and introduce to you our presenter, Janine Flagg. Janine is a field applications engineer here at EMA Design Automation. She has extensive experience supporting customers using Cadence design tools and as a PCB designer herself. Over to you, Janine.
Okay, so hopefully everybody can see my screen. I think I have it shared. Let's bring up the presentation and start it. Okay, so as Michelle said, my name is Janine Flagg, and I'll be presenting today's webinar, Constraint-Driven Design with OrCAD Capture, which is by EMA. EMA, a Cadence Solutions provider, is a full-service provider of EDA solutions, including software tools and consulting services. The focus of today's webinar is to introduce you to EMA's new Constraint Manager for OrCAD Capture. I will show you how easy it is to create electrical, physical, and spacing constraints using Constraint Manager for OrCAD and pass them directly to PCB Editor board file where they will be used to assist with the placement and routing of the board layout. I will also cover how we can pass elements such as the board stack-up and even XNets back to the schematic to be used during constraint assignment. Currently, most constraints are entered in the Constraint Manager in PCB Editor. The spreadsheet-driven interface makes it very easy to enter and review constraints. Adding certain properties in the OrCAD Capture Property Editor allows you to create constraint overrides in PCB Editor. However, not all constraints are available in the OrCAD Capture Property Editor, and the syntax required for some of them is not straightforward, which makes them difficult to add and review. Now we'll pause just a brief moment. Please take a second to answer the following poll question. Okay, are we back? Okay, so why EMA's Constraint Manager for OrCAD Capture? It is an integral part of the OrCAD constraint-driven flow. It allows the engineer to easily embed constraints directly into the OrCAD Capture schematic, which will then be transferred directly into the Allegro or OrCAD PCB Editor board files. This eliminates the need for paper documents and checking to make sure that the engineer's intent was understood and implemented by the layout designer. When added to the OrCAD design flow, CM for OrCAD provides an easy-to-use spreadsheet-driven interface for entering design constraints. CM for OrCAD offers a direct bidirectional interface to the Allegro and OrCAD PCB editor.brd files. With CM for OrCAD, the engineer may cross-probe between the Constraint Manager spreadsheet and the OrCAD Capture graphical schematic. This functionality allows the engineer to select nets in the schematic or constraint assignment in CM for OrCAD. It also includes a differential pair viewer that makes working with the physical constraints for differential pairs and visualizing the effects they have on the eventual routing much clearer. And what are the benefits of using CM for OrCAD? CM for OrCAD allows for seamless communication between the engineer and the layout designer. It allows for the reuse of constraints from design to design by way of technology and constraint files. Using CM for OrCAD saves time by finding and fixing potential problems early in the design cycle. This eliminates the need for multiple design reviews, so will shorten the overall design process. All of this will allow the engineering teams to reduce the number of prototypes needed and therefore more easily meet their project completion target dates. EMA's
You working on it? You want to put it in chat?
EMA's new CM for OrCAD provides you with a familiar spreadsheet-driven user interface that is so similar to the PCB Editor Constraint Manager that no additional training is needed. As in PCB Editor, constraints are contained within a hierarchical structure. Constraints that you specify at the top of the object hierarchy are inherited by the lower-level objects in that hierarchy. Constraints that you define at the lower levels of the object hierarchy take precedence over or override constraints defined at the higher levels of the object hierarchy. Cross-probing between CM for OrCAD and the schematic canvas is also available, which makes selecting nets for constraint assignment very easy. Excuse me. CM for OrCAD supports a set of comprehensive rules. This includes physical, spacing, and electrical constraints. The electrical domain is a powerful environment for electrical constraint entry, editing, and management. It includes wiring rules for scheduling, controlling stub lengths and parallelism, and layer constraints. It also includes maximum via count rules, impedance rules, min-max propagation delay, which is a pin-to-pin delay, total etch length, which is the overall length of a net, and relative propagation delay, which is a match delay. The physical domain includes minimum and maximum line width, minimum neck width, physical differential pair rules, line and buried via rules, T-junctions, and region rules. The spacing domain includes spacing constraints between all design elements, class-to-class rules, and region rules. CM for OrCAD supports the same set of comprehensive rules as the Allegro and OrCAD PCB Editor constraint managers. Elements such as constraints, net classes, net groups, and differential pairs may be sent directly back and forth between CM for OrCAD and the PCBEditor.board file with no need for net listing. You may also import the board stackup from the PCBEditor.brd file directly into CM for OrCAD. This allows you to set line widths and spacing rules based on the layer stackup. CM for OrCAD includes C-set designer, which allows you to create constraint sets. The concept behind constraint sets, or C-sets, is that very often you will have one or more nets, net classes, or buses in your design that all need to have the same rules. You can think of a C-set as a container for a collection of constraints. As an example, in the electrical domain, a single electrical constraint set may contain wiring rules, delay rules, impedance rules, and via rules. This makes it easy to assign all those rules at once to a single net, a bus, or a net class. Before we move on to the demo portion of the webinar, let's talk a little bit about the constraints required for differential pairs. Differential pairs constraints are set in both the physical and electrical domains. If you count all of those plus possible delay and match delay rules, each differential pair may have as many as 13 specific constraints assigned to it. The best way for the engineer to communicate all of these design requirements is to simply embed them into the schematic so that they can be transferred to the layout designer. First of all, let's talk about the differential pair constraints that are set in the physical domain. Min line width is the preferred trace width that should be followed most of the time, except when necking down between obstacles is required. The primary gap is the ideal separation between the two differential pair nets to be followed, again, most of the time. This is the edge-to-edge spacing that the two nets must have when not exiting pins or when not necking down between obstacles. The neck width specifies the line width to be used when the standard differential pair width cannot be accommodated. Likewise, the neck gap specifies the edge-to-edge spacing within the pair to be maintained when the normal differential pair spacing rule cannot be accommodated. The coupled tolerance rules allow the edge-to-edge spacing to deviate from the primary gap and still remain coupled. This is typically required in diagonal routing, where the gap will vary just slightly from the primary rule. Any spacing found within the range of the primary gap plus the positive coupled tolerance and the net gap minus the negative coupled tolerance is considered to be coupled. The minimum line spacing check may be used as a final sanity check to ensure that your differential pair nets are not too close together. This value may also be used if your differential pair spacing must be less than your default spacing rule set for line-to-line spacing. The minimum line spacing must be equal to or less than the differential pair net gap spacing minus the negative coupled tolerance. Next, I'll cover the differential pair constraint set in the electrical domain. The max uncoupled length rule takes the length of all of the uncoupled trace segments, sums them up, and checks them against the total. Checks the total against the rule. If the sum is greater than the allowable length, a DRC is created. As shown in the last slide, the differential pair may become uncoupled at some points in the final route. However, there are instances where this can be ignored. The gather control option may be set to ignore or include just the uncoupled trace from the pin to the first gather point. If the option is set to include, then the uncoupled trace length from the pin to the gather point is added to the total uncoupled length calculation. If the option is set to ignore, then the uncoupled trace length from the pins to the gather point is not included in the total uncoupled length. The phase tolerance value is used to check the differences in the total etch length of the two members of the differential pair. There are two modes for checking the phase tolerance. The first, static phase, is simply a check of the overall length of the two members of a pair. The second is the dynamic phase, which checks the length matching at each bend point. The differential pair viewer in CM for OrCAD helps you visualize how the physical design rules for differential pairs will affect the eventual routing of the differential pairs on the board. Once it is invoked, you may simply click on a layer in CSET Designer to show a diagram of the constraints for that layer. As you type different values into CSET Designer, the viewer will display the changes. It's now time for the demo portion of the webinar. Okay, so I'm going to bring up OrCAD Capture, and it has a schematic already opened. Now you'll notice once the Constraint Manager for OrCAD is already installed, you'll see a pull down that says Constraints. From here you can launch the Constraint Manager, you can exit the Constraint Manager from here. You can also remove Constraint Manager data from your existing .dsn file. I'm going to go ahead and launch the Constraint Manager now. Okay, so the Constraint Manager has as you'll notice, it looks pretty similar to the Constraint Manager in PCB Editor. It has pull-downs at the top that allow you to import, export things, set certain options, and so forth. You can also use the toolbars, the icon toolbars. So as an example, one of the options that I have set is I've enabled the auto update. This means that every single constraint I add in CM for OrCAD is automatically written to the .dsn file. I can also enable cross-probing both directions. I can search for things, I can refresh my view, I can create constraint sets, I can go into my viewer, my differential pair viewer. I can update CM for OrCAD from my board. Okay. I can also bring in constraint files and technology files. So if you have technology files that you want to use on certain designs that you've been using them in PCB Editor, they can actually be brought into CM for OrCAD as well. I can also update my board file. I can export constraint files, and I can export technology files. Okay. I can get help, and I can close the CM for OrCAD from here. So the first thing I want to point out is that we actually have bus elements here. Okay. If you haven't noticed, bus elements don't really pass to PCB Editor directly. So if we look in PCB Editor, this is the board file that goes with that schematic. We go into the Constraint Manager, you'll see the various bits of the bus, but you don't actually see the bus element itself. So I'm going to go ahead and close PCB Editor, and I'm going to update that board file. Okay. Now you notice I'm not net listing, I'm just going to update the board file with information that's coming from CM for OrCAD. Now I don't really have to close the board file, but it's writing to the copy that's sitting on the disk, so I would have to reopen it again. So I'm just going to do it this way. Okay, now if I go into the Constraint Manager, you'll see that we now have buses. Okay, so all the buses that showed up in CM for OrCAD are now in PCB Editor. This actually makes it easier to apply constraints. So the first thing that I'm going to do is create some constraints. I'm going to create constraint sets because that makes it easier for me to apply a bunch of constraints to elements at the same time. I'm going to select the electrical domain, and then I'm going to create a new electrical C set. And I'm just going to call this rules. I'm going to start with the wiring worksheet. I'm going to select a topology. I want a min daisy chain. My stub length, I don't want more than 200 mils of stub length. And I'm going to set my max exposed length, or the length that I can route on the external layers of the board, at 200 mils as well. Now I'm going to move on to via rules and set my maximum number of vias at 2. I'm going to set my impedance at 60 ohm target with a 2 ohm tolerance. I'm going to set my min-max propagation delay. By doing that, I'm going to select the longest to shortest pin pair. And I want my minimum length to be 1,000 mils and my maximum to be 3,000 mils. Okay. That's all I'm going to create with or add to this constraint set. I'm going to create one more constraint set that we'll use a little bit later on our differential pairs, and I'm just going to call it DP. Okay, let's go to our diff pair rules. I'm going to set my maximum uncoupled length to be 200 mils, but I am going to ignore the length between the pins and the first gather point. My static phase tolerance I'm going to set at 25 mil. My dynamic phase I'll set at the maximum 0. I'm going to make it 0 actually, and then set my tolerance at 20 mils. Okay, so I've finished setting my electrical constraint sets. Now I'm going to apply them. So I'm in the electrical domain, and I'm going to go to my D bus, and I'm going to set my rules constraint set. Now you notice I apply it at the bus level, and each bit of the bus inherits that rule set. So one other thing that I'm going to do is I'm going to select the nets in my VD bus, and I'm going to create a matched group with them. Okay, I'm just going to call it VD underscore M group. Okay. So let's go all the way to the top. Here's my matched group, VD matched group, and I'm going to set the constraints for it. Again, I'm going to set it at the group level. So I'm going to choose longest to shortest pin pair. So it will select a target net, which will be the longest. My scope is going to be global, so it considers the entire net. My delta I want to set at 0. And my tolerance I want to set at 25 mils, or 25, actually I want to set at 25 mils, not 25%. So there we go. Okay, so I've set my electrical rules. Let's go ahead and update the board file again at this time. You notice again I don't have to net list. I can just update the board file directly. I'm going to go into my status and update DRC, seeing as how I just read in a bunch of new constraints. And I can see I've now created 24 DRCs. I can click here and get just a quick view of what my DRCs are. So I have a bunch of relative propagation delay, so that's my match delay. And my propagation delay, I have a minimum via count issue, impedance rule problems, and my maximum exposed length is violating my 200 mil constraint. So I'll zoom in a little bit, and I'm going to select my min via count, or my maximum via count from here. Okay, let's just choose that one, and you can see, yeah, my maximum via count is saying that it's supposed to be 2 and I have 3. Well, I can't remove this one, but let's look up at the other end of the trace here. I can remove this via here. Okay, let's go ahead and route this directly through to this via, where we removed one via. Now we still have another error here, and this is our maximum exposed length. It's supposed to be no more than 200 mils, and it's 260 right now. We actually shortened it some by getting rid of that, that other via. But let's go ahead and use the slide command and move the via over. Okay, so we got rid of that problem. Before we move on and fix any more, let's go ahead and look at the constraint manager. If we look at the wiring rules, we've actually corrected them now. So by the way, if you ever want to know exactly what your margins are, you can just click and select Analyze, and it will analyze your issues. I corrected the via problem. we have a bunch of impedance issues and our min-max propagation delay and our relative propagation delay. Okay, so if I analyze this, we can see it's choosing the last bit of the bus, VD7, as the target. So it's apparently the longest. Okay, I can go in and fix just a few of these. I'm not going to fix all of them right now. But if I go into Delay Tune and I start adding length, you can see, if you look at the very right-hand bottom corner of my board, you can see that it's showing me my delay. And as soon as I meet my delay, you'll see the meter turns green. Okay, so I can go ahead and add as much length as I need to go ahead to get rid of those constraints or to get rid of the DRCs. There we go. So that's enough for now. Oh, our impedance. So if we float the cursor over the DRC, you can see that it's supposed to be 60 ohm, which is what we set in CM for OrCAD. And it's actually more like 81, which means we have to make our trace a fair amount fatter. So it's complaining about the ones on the top layer. So let's just do an edit change and set these trace widths to 10 mils. And there we go. Okay. So the last of our issues over here is our relative propagation delay. Now, if you look, the delay is actually showing up over here, or the error is showing up over here, which isn't even exactly on the same net. That's because these are XNets. So I mentioned XNets earlier. For those of you who don't know what an XNet is, it's an extended net, which is a signal path that traverses a discrete passive component, such as a pull-up resistor or something. So this is an XNet. It actually traverses this discrete component. Okay? So when I select when I float my cursor over the DRC, it's highlighting the net, or the XNet, that's too short, and it's telling me it's too short. And the other one, it's highlighting the one that it's supposed to match. Okay. So again, I can just go in and I can add some delay tuning. Okay. As soon as I add enough delay, my meter turns green. Okay. And so that's exactly what we needed to do. So it easily tells us what the issue is. And by the way, I don't really have to, I could actually add the length over here if I wanted to, because that's part of the same XNet. And we're actually constraining the entire XNet, not just the separate nets. Okay, so this is enough for now. Let's go ahead and save my changes. And we're going to exit out of PCB, and we're going to go back to the Constraint Manager for OrCAD. So the next thing I'm going to do is I'm going to import information from my board, so that, because I need my stack up, I'm going to create my physical rules for differential pairs. Okay, so let's go ahead and choose our board that we were working on, which is our Constraints Update board. I'm going to merge my constraints with existing constraints. So if I had constraints in both places, it will merge them. Okay, so now if I go into my physical domain, you'll see that it brought in my default constraint rules. And when I go in to create a constraint set, let's go to the physical domain, it shows my default rules again. And when I go to create a constraint set, oh, by the way, it shows the stack up as well. So it brought the stack up in from my board, which means that now I can constrain, I can actually create physical and spacing constraints based on my stack up. So I'm going to create a differential pair constraint set in the physical domain. I want my min line width to be 5 mils, except on the top and bottom layer. It's going to be 8. My neck width is going to be 4 mils on every layer. There we go. Let's see. My primary gap is going to be 5 mils, except on the top and bottom layer where it will be 8. So that means that on my internal layers, I'm going to have 5 and 5, and on my external layers, it will be 8 and 8. My net gap is going to be 4 mils on every layer, and I'm going to set my plus and minus, my positive and negative tolerance to 0.5 mils, which makes my minimum line spacing 3.5 mils, because that's my primary gap, or my net gap, minus my negative tolerance. Okay, so we've just created a constraint set, a physical constraint set for our differential pairs, and we already created our electrical constraint set earlier. So now that we've created this, we can actually go in and take a peek at what they're going to look like. We'll look at our differential pair viewer. And as I zoom in, you can see that my line width is 5 and 5. My neck width and gap is 4 and 4. Okay. You can see my minimum line spacing is the yellow line, and that's 3.5. Okay. Now, if I go to the top layer, select the top layer, you can see that my min line width and primary gap have changed to 8 and 8. Okay. Neck width and neck gap are still 4 and 4. So this easily allows you to check every layer of your design and make sure that everything is what you expect. Okay, we can exit out of CSET Designer. And first, before we can apply our rules, we actually have to define our differential pairs. So the easiest way to do that, I'm going to go back to my schematic, go to page 1, and here's all my differential pairs. So I can select them at the schematic, bring up my constraint manager again, and they've been selected here. I have a couple groups of nets that are all differential pairs. So I'm going to go ahead and create diff pairs. So my first filter is _P, so for my positive side. And for my negative side, I have an _N. I want to name my differential pairs with the prefix of DP _. Then I'm going to click Assign Pairs. So it gives me a chance to review them before I'm actually saving them to the database. So I have DP _ at the beginning of every differential pair name. So it's DP _ plus the signal name. Then I have the first net and the second net. Let's go ahead and save those. Let's go up to the top and close up our buses. Then we can see all of our differential pairs. I'm going to go ahead and compress them. And then I can assign the rules. Assign our differential pair rules. Okay, so you can see they've been assigned. And one other thing, we have to go into the electrical domain also and assign the differential pair constraints in the electrical domain. Okay, so there's our electrical. So we have our differential pairs assigned. The last thing that I'm going to do is go in and set some spacing rules. Okay, so we have 2 net classes already. We have our clock nets and we have our DC nets, which is our power and ground. And I'm going to create one more net class. And my net class is going to consist of my VD bus, so which is XNet. So I'm just selecting all of those. I'm going to create a class, and I'm just going to call this VD nets. Go up to the top, and here's our 3 net classes. Okay. Now I'm going to create some spacing constraint sets. So let's again open up CSET Designer. We'll select our spacing domain here. You can see we have default spacing constraints already set. And we're going to create actually 3 constraint sets. So the first one is going to be 8 mils. Easiest way to assign everything to 8 mil is simply select the first field, drag your cursor all the way over to the side, and type in 8. Everything gets filled in. Okay, I'm going to create another one. It's going to be 10 mils. Again, select the top, scroll all the way over to the side, and type in 10. And we're going to create one more, which is going to be 12 mil. Okay, there we go. So now we have 3 different special constraint sets plus our default constraint set. I'm going to exit out of here, and we're going to go to our spacing domain. So I'm actually going to leave everything with default spacing right here, but I'm going to create some class-to-class rules. Okay? So everything can have default except when certain signals run next to other specific signals. So I'm going to create some class-to-class pairs. So the first pair I want is between my clock nets and my DC nets. Okay, so I can click there to specify I want that pair. I can hold down my control key to where I can select multiples to create at the same time. I want another one between my clock nets and my VD nets, and then one more between my DC nets and my VD nets. Okay. I'll click OK. Creates the different pairs, and now I can assign the rules. So between my clock nets and my DC nets, I want 8 mil. Between my clock nets and VD nets, I want 10. And between my DC nets and my VD nets, I want 12 mil. Okay, so, and that's all the constraints I'm going to create for right now. I'm going to go ahead and update my board file again. Okay, so open up the board file. And let's go to our status, update the DRC, and you can see we have 6 issues. So we have our original 4 propagation delay, and then we have a couple of line to surface mount pad. So that's our needs 12 mils and has less than that. Okay, so it's telling us exactly what the issues are. And here's our problems right here. So we can just use our slide command and push these guys all over. Okay. So in last, I'm going to show you a little bit of routing. Since we added all those rules for our differential pairs, we can now go in and route the differential pairs. Start out on the top layer and click to add vias. Select a via pattern, vertical via pattern, and then place. If we zoom way in, you can see that it's definitely different line width and spacing on the top layer as there is on the internal layer. Let's come back out and go ahead and route this. Okay, and I'm not going to route all of them. We'll just route a couple just to let you see what it's. And if you look over to the bottom right-hand corner, it actually, again, is showing my little meter, And the meter is letting me know if I've met my, my phase tolerance. Okay. So we can see I'm off here a little bit, not off enough to get an error, but straightening those out will definitely make a difference. Okay. So that's the end of the demo portion. I'm going to hand it back to Michelle for, I think she has another poll question for you, and then we can do some Q&A.
Yes, thank you, Janine, for that great demonstration. This is Michelle again, and before we launch the Q&A portion of the webinar, I just wanted to run one last poll question to get a better idea of what webinar topics you guys would like to see us host in the future. Please take a moment to provide some feedback, and we will move on to the Q&A in just a minute. Okay, great. At this time, I would like to open up the floor to the Q&A. If we are unable to address your question immediately, we will be in contact with you outside of the webinar. Just a reminder to all attendees, this webinar will be recorded and posted on the EMA website within the next few days. We will also email all attendees with a link to the webinar for reference. Okay, so. The first question we had come in is, are these constraints contained in a separate file?
No, they're actually contained, they're fully contained in the .dsn file, so the capture, the OrCAD capture.dsn file.
Okay, great, thanks. And what version of OrCAD does this work with?
It works with 17.2 only.
Okay. Got another great question here. Will this work with Allegro PCB Editor, or is it just for OrCAD?
It works with both Allegro PCB Editor and OrCAD PCB Editor.
Okay. And another one, what if we outsource layout? Can we still use this to define constraints?
Yes, if they're using PCB Editor, either Allegro or OrCAD PCB Editor on the back end, you can still add your constraints here. They'll be able to see them when they open up the .brd file.
Okay, and another one here, can I reuse these constraints on multiple designs?
Yes, you can. So you can save off either technology files or constraint files. So technology files would save off pretty much everything, so all the constraints and even the layout or the stack up if you wanted to. Constraint files, you can kind of pick and choose which constraints you want to save off. And then they can be read into either CM for OrCAD when you're starting a design or at the board level.
Okay, great. Is there any other questions anyone wants to address today? Please put them in the questions panel. If we're unable to get to them right now, then we will be in contact with you shortly. Okay, got one more coming in here. Is the DSN file with embedded constraints compatible with Capture without the constraint manager? So can someone without the constraint manager for OrCAD add load the DSN file?
Yes. Yes, they just won't be able to see all of the constraints that were added in the CM for OrCAD. Some of them will show up in the property editor, however. So yeah, it's still compatible with regular OrCAD.
Okay, great. Okay, well, thank you, Janine. It looks like we're about ready to wrap up here. If you guys have any questions we haven't answered yet, we will be following up with you on an individual basis. I will be closing the webinar now, and we will be sending everyone a recorded version of today's webinar with the slide deck within the next few days. Thank you all for taking the time to join us today.